these structures, kind of as a domain space, there are two somewhat complementary ways of doing it. Either you take like a given triangulation of your space-time, so some space of given topology, and then you allow the edge lengths to vary. So these are then the dynamical variables you're integrating over in the path integral. So these L variables. Alternatively, you could fix the length variables to one or two values. So all of them. So you have basically just a bunch of identical building blocks, and then you could change the way you glue these things together. So in both of these ways, you would then hope to kind of cover in some ergodic manner the space you're interested in. So well, there are certainly rough arguments you can make that in this way you're not leaving out kind of huge chunks of the configuration space of four-dimensional curved geometries. So there doesn't seem to be anything very intrinsically wrong with either of these statements, either of these choices. I explained to you that the second choice, which is also called dynamical triangulation, because you're just changing. I mean, the triangulation itself becomes kind of the dynamical variable, has a bunch of advantages. And for example, in 2 dimensions, you can analytically solve some of these models. And well, also there's more to this story, which we'll learn more about today and tomorrow. At the end of the lecture yesterday, I also raised the issue of two things one can do. One is writing down kind of non-perturbative Lorentzian path integrals, where you're then summing or integrating over complex amplitudes, and which I then said, well, it tends to be really difficult to perform, I mean, in a mathematically halfway clean way, as opposed to something that's called Euclidean quantum gravity, which, as I pointed out, is a priori a rather different problem, is a path integral, where you're integrating over all positive definite metrics, or geometries, I should say. And the reason why these were two different things is, I mean, one of the reasons is that these Euclidean structures, of course, they don't make any distinction between space and time direction. So if you are in a Euclidean space-time, in inverted commas, it's, of course, as easy for you to move backwards and forwards in time as it is to move right and left and front and back. So there is no distinguished time direction. There is no causality. Of course, there are no light cones. So it lacks structure compared with the Lorentzian case. And you wonder how this will be retrieved if you are not putting it in somewhere into the path integral. Of course, it could just turn out that no matter what you do, in the end, you can show that somehow the results are closely related or equivalent. But of course, the trouble with these path integrals is that we tend not to be able to say anything very much about them at all. So they are just very difficult objects to handle. Although we meet very soon a concrete example, and it's exactly in the framework of these dynamical triangulations, where you can do the path integral for Euclidean signature, so Riemannian signature, and for Lorentzian signature in 2 dimensions. And you can solve both of these things analytically, and you can show that they lead to inequivalent results, which are also not related by any simple, sticking the right factors of I somewhere. So that was, to my knowledge, kind of the first example that was given that was very explicit, that said, look, if you're doing it the Euclidean way, that's a priori, well, what should it have to do, with the Lorentzian? That was just a theoretical argument, but there are now, explicit examples where you can see, well, it just gives you something different. And maybe, not so surprising if you consider that it's just physically rather different objects you're working with in either of these approaches. Okay, now, what are our expectations? So what should happen in the best of all worlds? I have a non-perturbative path integral formulation. And of course, going back to the very beginning of the course, what I said we'd be looking for is a kind of a quantum dynamical principle. And its solutions should then tell us everything about quantum gravity. And also it should tell us about what quantum space-time is. So that's really, the analogous logic you're using here, also comparing to the classical theory. You have quantum equations, you solve them, and then, well, they tell you something about space-time, including what happens at the very, very shortest scales, so Planck scale, typically. So what do we expect to find, with all the knowledge we have of quantum theory and GR? So we expect a solution to the kind of quantum Einstein equations. To have, well, two properties. Or should satisfy the following. So firstly, you should think, well, what happens, just these hand-waving arguments, when you go to very, very short scales? Well, somehow, quantum fluctuations of your degrees of freedom, in our case, these are the geometric curvature degrees of freedom, should be significant. And of course, then you'd not expect, and this is just saying the same thing, that the description in terms of smooth assignments G mu nu will be anything like appropriate. So then people wave their hands and say, oh yes, and space-time, it will just fluctuate wildly, and it will form foams and bubbles and what have you, and they draw nice pictures. And of course, this is just artistic impressions. The question is, of course, can we find a quantitative framework which would tell us what space-time is, and which would allow us to check whether any of these mental images we might associate with quantum foam or space-time foam are actually feasible and have a chance of being correct. But anyway, so on short scales, no, I should say quantum space-time. Nice equations. Einstein equations. So this is what I before called a quantum space-time should be. So strongly quantum fluctuating microscopically. And by microscopically, of course, I mean really, on length scales of the order of the Planck length. And on the other hand, if you go to sufficiently large distances, you really want things to look more and more like classical spacetimes. So resemble a solution to the classical Einstein equations. Macroscopically. And of course, macroscopically could be even still reasonably close, quite close to the Planck scale, wherever a classical or semi-classical description, maybe in terms of G mu nus, will be appropriate. Now, it turns out that if you're talking about kind of non-perturbative approaches, where, for example, you just try to compute the sum over all spacetimes that are already kind of, as I explained in the path integral, generically very far away from classical solutions, something that has wild quantum fluctuations is, well, that's not a problem. You can just invent many prescriptions that seem to be doing this. What, however, then is a genuine problem is to show that on large scales you retrieve anything like classical spacetimes. So this is really here the difficult aspect, to cook up some Planckian model or to postulate, some structures at the Planck scale and some dynamics for them. Well, you invent one, I invent one, the person over there invents one. But then, well, of course, to make it quantitative, again, is another story. But also then, in addition to show that on large, there is a well-defined classical limit to these things, it turns out to be very, very difficult. So that's a bit the opposite of what happens when compared to, say, doing a perturbative quantization of gravity. Because if you do a perturbative quantization of gravity, you're bound to discover the special classical solution, I mean, you started out with. So the issue of the classical limit tends to be, I mean, very straightforward. Of course, how to account quantitatively then for fluctuations that are maybe far away from this? Well, then you run into the problem of non-renormalizability and related issues. But so here it's a little bit opposite if you really go for such a non-perturbative approach. So this is clearly must be a big concern. For any kind of Planckian dynamics, you construct, pull out of a hat, postulate to be there. But how can you even understand that you might have a problem? Well, that's a legitimate question, and it's a good question because we don't have any complete theories of quantum gravity yet. So, of course, that also entails, well, that we are a little bit freely floating as to what the theory is about or might be about. And of a theory which you don't really know what it exactly is, it's of course difficult to say anything about any classical limits. But there are, fortunately, I mean, some concrete models around where you can just try to address this issue. And then interestingly, what you're finding is that there are some generic things that tend to go wrong. So you can just write down things that look very nice, pen on paper, expressions for path integral, formal integrals, and sums. But then in cases where you actually have some quantitative tools to kind of numerically evaluate, say, what these path integrals are and do and what behaviors they have, you find that there are some generic troubles that keep popping up that are rather independent of very specific ingredients of your approach. Now, in order to make such statements, you do then need such quantitative ways of evaluating the path integral. And what has turned out to be extremely important here is to be able to approximately compute the path integral. And to do this, you need specific numerical method. And I will just highlight one briefly for you that goes by the name of Monte Carlo simulations. So that is just kind of a systematic way of trying by, as one said, I mean, a random importance sampling to try and establish the value, in this case, of a certain integral by computational methods, and which is kind of systematic and well-defined. Of course, gives you only results with error bars, with numerical error bars, and all technical numerical problems that are associated with these methods. But of course, we should keep in mind, for example, that if you look at certain non-perturbative properties of QCD, such numerical methods have provided us with enormous richness of data, and which seem to just describe nature very well. So they are clearly a legitimate tool, but not only legitimate. I think there are currently situations in physics where you cannot make any progress without such methods. So let me just briefly flash. I call this Monte Carlo simulations 101, and it will just take 5 minutes. Just to sketch, what one is doing here as a matter of principle. And of course, these are tools that are also being used elsewhere to understand non-perturbative aspects of quantum field theories, also beyond just the physically important cases of QCD, say. Okay, so what you do, the idea is that you set up a random walk in the space of configurations that's relevant to your problem. So, for example, that could be, in our case, the set of all, piecewise smooth geometries of some dimension. Of course, these systems must be finite, otherwise your computer cannot describe them. You cannot describe systems with infinitely many elements in them. So, for example, let us fix, for our case, of a given volume n. So for us, this would be just, say, the number of building blocks. So think triangles in 2 dimensions, for example. So in such a way that the probability distribution of the configurations asymptotically approaches the Boltzmann distribution that comes just kind of from the action, or a Wick-rotated version of it approaches distribution 1 divided by z. So z was just my expression was a full path integral, or the partition function. So this works in Euclidean signature. So in our concrete case, it's this 1 over ct, e to the minus s of tn. So I'm specializing, to the case where I'm sitting on this configuration space of dynamical triangulations. I'm fixing the volume to be n, and then I take the partition function. It's just the path integral over all of these, where I work with weights e to the minus s. So these are kind of Euclidean real weights. And you see, this is a probability distribution because I've normalized it here by the entire path integral. So this is what this. Then you're setting up a random walk that has these properties. And what you then do, so you get a kind of, a sampling where your random walk is concentrated in regions where this probability is large. So exactly kind of proportional to this distribution. So it's kind of maximally effective, right? So it spends a lot of time wherever this weight here is large. And then what you do, you evaluate observables, or rather their expectation values. Expectation values. So some geometric quantity that depends in some way on the ingredients of your lattices, your simplicial triangulations. So you take, this is kind of the object you'd like to evaluate, theoretically speaking, e to the minus s of t. So where this is still some infinite sum. Now what you're doing with your Monte Carlo simulation, first of all, you have either length cutoff or you fix a volume n. And then, of course, you just sample this space. So you approximate this through some finite sampling where you then compute in an approximate way this expectation value by kind of running the measurement n times, O of t a. So this is now a limited set of measurements. I'm making this little n measurements, where I have to be careful that these TAs I'm sampling at are kind of statistically independent. Configurations. And of course, I will get a result that is the better, the larger this little n is, for sufficiently large n. N is the sample size. So this is a very concrete prescription. And it's of the kind that kind of the errors one makes here, will be suppressed, of course, the larger this little n is. They will be suppressed like 1 over square root of n. So if I make the sample 4 times as large, I will reduce my errors, my numerical errors, by a factor 2. So that's essentially how it goes. Now, what one then has to do, yes? Oh, yes, that's a good point. Practically, well, there is a way, because I haven't told you, for example, how you store these triangulations in the computer. And the actual way you do it is usually you make them into labeled triangulations. And then kind of the way you then factor out by the labeling, which is, of course, totally arbitrary, takes exactly care that you automatically really produces 1 over CT. So there is really a way in which these exactly take this into account, these methods. Now, the way I move around in this space, in my random walk, is defined by a set of moves. So that is just, I give you a triangulation, and I make, in this case, a local manipulation that changes it to an inequivalent triangulation. And so this is still needed to make this algorithm complete. So ergodic is kind of a technical term that means that you can get from one configuration to any other by a finite sequence of these moves. And of course, you have to show that they exist, or that there are one or many suitable sets of implementing them. So you must be able to get to anywhere in your configuration space by these moves. To go from any triangulation T to any other T prime in a finite number of steps. So let me just give, for illustration, say what is a set of such moves that satisfies this in 2 dimensions for these dynamical triangulations in Euclidean signature. So all you have are equilateral triangles with some edge length A. So what is one of them? One move substitutes one of these triangles by 3 of them by inserting a vertex in the middle. And, so that one triangle becomes 3 triangles. But you have to keep in mind that each one of these triangles, although I'm now drawing it not isometrically on the blackboard, is exactly the same as this triangle. So it's just my unit triangle with the same edge length. So if I wanted to embed it isometrically in 3 space, it would pop out this corner here. This is called the subdivision move. And the other one takes a pair of triangles which share one edge and flips the edge. So it becomes this here. So you keep the 4 outer edges, if you like, and just rearrange the geometry. So this is a flip move. And what you always also have with these moves are their inverses. That means if I can identify such a local configuration on my lattice, I'm able to substitute it then. So that move is part of my set by a single triangle. So end inverses. And such moves, are well known, also well known to mathematicians. They exist in high dimensions also. One way of implementing them are the so-called Alexander moves, just in case you've heard the word. I'm not going to explain them here. So you do this now, you see, and so you evaluate certain observables. Of course, it becomes the better, the larger your lattice is, so the larger your capital N is, and the larger your sample size is. And of course, the larger the sample size means just your computers are running longer and longer and longer. And of course, then, the paraphernalia of how do you set in an optimal way, set up in an optimal way and efficient way, a computer simulations. Well, that's the whole subject in itself. So this is just to give you an impression of what one is doing. And what one then does as a matter of principle, these systems are all finite, but you're really interested in the n to infinity limit. Right? So what one then does is, for instance, one studies these observables, and one tries by systematically changing this capital N and making it larger, extract kind of a systematic scaling behavior that these observables may or may not have. Right? So, and you're typically interested in observables which have a specific scaling behavior, because it then gives you an indication that there might actually be a well-defined theory lurking in this limit. That's kind of part of a continuum limit, so where I have just removed my regulators. So, and the technique for extracting in a systematic way kind of physical behavior, so this kind of scaling, is called finite size scaling. So kind of trying to extract the physics of infinite n from studying systematically, the situation where n becomes larger. Now, can we make this concrete? Well, that's the whole nice thing about this formalism. Yes, so what is, you should say, show me a nice observable from which I can read off interesting behavior of my quantum theory. So here is one. So that's, so here's an example of an observable, just in this sense, just defined up there, kind of characterizing quantum geometry. So quantum geometry is really now kind of what comes out of the path integral, what is given to you, by this superposition, this very large superposition of all these highly fluctuating geometries. So the observable we are going to look at is the so-called Hausdorff dimension. Call this D with a subscript capital H. And although, well, a dimensionality, you could say, is something pre-geometric. I mean, before I start talking about the metric. But of course, it can be extracted from looking at, say, by comparing volumes and lengths. That's essentially what underlies this here. So what you do is the following. You're sitting on your triangulation. You pick a point. Well, of course, you random walk. You set up a random walk in the space of all triangulations. So you pick a 4 geometry. Then in that geometry, you randomly pick a point. And then you walk out in concentric circles away from this chosen point. So what it looks like in a triangulation, now in 2D, just for illustration, is something like this. So let me just draw some piece of triangulation. And just imagine it was equilateral. Of course, I cannot draw it in this way on the blackboard. So let my point be this one here. Now, I am looking at an analog of what one would call a geodesic ball in the continuum. And what that just means in the continuum just means, I pick a point in a Riemannian space, and I just look at all points that are a given geodesic distance away from that. And then I look at how much volume, lies inside this shell. And I do the same here. And of course, very natural units I have here are kind of geodesic steps of length 1. So it's just going one lattice link further. So what is a geodesic ball of radius 1? Is everything contained within a single lattice length. Yeah, so it's just everything that lies in here. Okay, now I should draw this a bit larger. Right, so now what then by contrast is contained in a radius 2 would be this thing here. Well, everything I've drawn here. It's a bit too regular what I'm doing, but here you get the idea, right? Now, in each step, I can now measure the volume. So, and I do this now in many steps. So I walk and walk and walk. And for each step, each geodesic distance, 1, 2, 3, I measure what the volume is. So what I'm getting is kind of data as a function of r, where this is now an integer. Just a sec. Now, what I do, so now I have just done this at one point in one geometry of my ensemble. Now, I compute an expectation value, which means I'll randomly, go to another configuration, and I pick another random point in that one and repeat the process. So, and of course, in this way, then I really get to an expectation value of this quantity. And then what I do is I try and understand how this scales to leading order as a function of r. And the exponent here, then, I call the Hausdorff dimension. And it gives me a piece of geometric information. Of course, if I do this on a regular manifold, kind of locally, then this will always reproduce the topological dimension for me. Okay. But the beauty of this is, this gives you some information in much more general spaces. And in particular, there is no particular reason why, when I'm in an ensemble of highly quantum fluctuating geometries of this type, once I go away from the scale where everything is just dominated by kind of the lattice discretization, so somewhat larger scales, that this dimension should be equal to the dimension of the building blocks I put in the first place. And what one actually finds is that generically it's not. It's something else. So the dynamics of these things plays then a crucial role in determining what this Hausdorff dimension is. And of course, it gives me one piece of information about what geometrically my quantum geometry is. Yeah, there was a question here. Yeah.
Well, I'm not sure if we can go with those ergodic moves. We can go from any configuration to any other, because those moves, those moves conserve the boundary dots, right? The number of them.
No. What do you mean by the boundary?
Those dots which are surrounding a lattice.
Yeah, but there is no,
I cannot change the number. Right?
No, but look, if you mean this here?
Right. Yeah.
Yeah, I could make a next move. I make a flip move with this and its neighbor, and whoops, this would be gone. So clearly, I can change this.
Right, but there should be a neighbor there, right? Well, is it an infinite set of lattice points, or is it closed?
Yeah, so this should be sort of, I have now a big, say, two-dimensional triangulation, and then I locally apply to simplices, local configurations that look like this or like that, I apply this move. And then I get a new big triangulation, which is just differs, by these steps. So there's nothing that is particularly conserved. So there is no obvious thing I see, that's, well, there isn't. So otherwise I wouldn't tell you that these are ergodic moves.
Okay.
So maybe you, think about this again. So this is something very, so what is so nice about it is very geometric, it's very explicit, and you can just evaluate it, by these Monte Carlo techniques, and you can get rather accurate results about what this is, and it gives you some first idea of the type of spaces you're looking at. So now what happens, for example, so that was done in for the path integral in terms of kind of these Euclidean dynamical triangulations. In 4 dimensions. So this just means I start with 4-dimensional building blocks and I glue them together so that they look locally like 4-dimensional simplicial manifolds. I can make these measurements. And, well, what happens? So it turns out, what happens turns out to depend to some degree on the values the couplings have in my action, right? I have now action weights, e to the minus s, but remember, s depended on at least a couple of constants, so Newton's constant and lambda. Now, here I told you I can do, for example, I can look at things for fixed volume, fixed n, then this lambda actually drops out as a free parameter. So I'm just interested in dependence on G Newton, the bare coupling, as one says. So dH depends now on what Gn is, but only in a very rough sense, that we have a phase diagram. And the phase diagram it's handy to work with the inverse Newton coupling, because that is the object that appears in front of the action. It's the inverse Newton constant. And then see what happens. Now here I'm now drawing a phase diagram which has the lambda still in it. And the corresponding path integrals is a fixed volume path integral, and the one where I leave the volume free, they're just related by a Legendre transformation. So it's very easy to go from one to the other. So here is, now I'm going to draw what is called a phase diagram, which gives me a rough characterization of different phases of the system. So what happens as a function of these two objects, two variables? First of all, there is a critical line. And the critical line, it turns out, is the one where this n equal to infinity limit exists and can be taken in a meaningful way. So that means all interesting physics is only found along this line. Only when you fine-tune to this line do you get appreciable contributions in your path integral from things with very large volumes, as you want, because you want to get rid of this. This is kind of a cutoff that you're having. So, and what then happens on this critical line? So this is line. You have to tune to. So here you can now just vary the inverse Newton constant, and you find two phases. So there is a transition point, kappa naught critical. And what dH is depends on whether you're to the left or the right of this. So what you find here is called a crumpled phase. I'll just tell you in a second what this means in terms of geometry. And what you find over here is a kind of a polymer phase in terms of branch polymers. And this turns out, so the crumpled phase, has a Hausdorff dimension that is infinite. And the polymer or branched polymer phase has a Hausdorff dimension that is always within measuring accuracy and taking into account that we're working on finite lattices, that is 2. So you'd say this is rather bizarre, right? You start from 4-dimensional building blocks, you put them together to get simplicial manifolds, which are locally 4-dimensional. But then, when you make these measurements, you find Hausdorff dimensions which have nothing to do with 4. Okay? So that's the first kind of non-perturbative surprise. And you might ask, well, how is it possible? Well, first of all, it's possible because, of course, we are invoking a non-trivial limiting process. Right? And then we're looking away from the scale. I mean, when we look at computer data, we look away from the scale that is just the lattice scale. Because if I'm just looking on the scale of the lattice cutoff of single edges or 2 single edges, all I see is, of course, what I've put in. So measuring things at this level, I would always find a Hausdorff dimension of 4. But of course, in the continuum limit, these things will, of course, shrink, and, well, they will be irrelevant. So only what's relevant are kind of physical distances where kind of infinitely many of these contribute. But of course, on the computer, you cannot do this. But what you identify on the computer is just a length scale that is sufficiently far away from these discretization artifacts, the lattice artifacts. So it's bigger than that, but is also away from the maximal size that is possible on any given lattice. Because then you get finite size effect from the, because your lattice is finite. Although you would like it to be infinite, it has boundaries, or it's topologically, it closes on itself, something like this. So then you get finite size effect. So in between those two extreme regions, which are contaminated by, just the parameters of your computational approximation, your numerical approximation, you try to identify kind of a region where you trust your data as being representative of the n equal to infinity limit. And of course, this is kind of a subtle game, but just to give you a rough idea. And this picture emerges totally clearly. Now again, how can it happen? It's what I would call an entropic effect. So it has rather little to do with the weights of the individual geometries than with how many times a given value of this weight is realized as a geometry in your path integral. And there it just turns out, depending on whether you are here or here, there are kind of characteristic geometries that totally dominate your path integral. And what are they here? On the left, in the crumpled phase, there are configurations where all of your building blocks, they condense around one or a very few vertices. So everything wants to cluster together for some entropic reasons. I mean, So you get, things where little, I don't know what to call them, hedgehog geometries, where all, you put in thousands and thousands of building blocks, but they all want to share, one and the same vertex. Of course, in this manner, you never get anything that has a macroscopic size, because the diameter of this object will be always on the order of, 1 or 2 lattice links, because they all want to be a neighbor of that one vertex, or a couple of vertices. So, and please realize, that this is a characteristic of a space with very, very many dimensions. There's a lot of volume in a very small diameter. Yes, so, well, this explains this number here. Now, by contrast, what happens on this side of the phase transition is that preferably the building blocks, they want to align along one-dimensional kind of polymers that themselves branch. So a picture, would be, well, that's a branched polymer, right? So it's something that is locally one-dimensional, but at any point, kind of branches can occur. And such an object, well, these are objects that pop up all over the place, but they have Hausdorff of dimension 2. So, well, how to understand this is somehow the branching at every point accounts for the fact that it's 2 and not 1. Of course, locally, these are kind of one-dimensional. But the fact that they can branch out everywhere contributes to this kind of volume versus radius effect that produces the leading power of 2. Yes, what's the question?
Yeah, I was just going to ask about this polymer phase. Like, why is 2? I didn't understand why it's not like 1.5.
Well, this is just how it comes out. I mean, it's an outcome. Yeah. What I wanted to say is, of course, for a long time, or for some time, I should say, it wasn't understood, well, what the geometry was. I mean, you start with some prejudice that what you're getting can in some way be interpreted as a macroscopic 4-dimensional space. And yeah, if you have this idea, then you start making all kinds of measurement before realizing that, oops, actually I'm not at all talking about a space that is 4-dimensional in any sense of the word. But once you've uncovered that, of course, you can then try and go back and try and understand what it is. And then this is exactly what people then did. They looked in their simulations and they tried to understand what are these typical geometries. And then you form a hypothesis. I mean, of course, the computer doesn't spit out pictures for you. It just spits out a bunch of ones and zeros. And you have to ask clever questions, for example, about the distribution of vertex coordination numbers. I mean, when you do this, of course, and you see that in this space you have a huge peak, at a very small number of vertices. But you have to ask the right question. I mean, it's not that, it doesn't talk to you. You have to identify the right observables to measure. But once you've done this, you can then come to conclusions like this. And once you then know that what you're talking about is a branched polymer system, branched polymers appear in many contexts, just as statistical mechanical systems. But of course, here, you're not so very happy about them because they don't appear to have any legitimate, whichever way you look at them, interpretation as extended 4-dimensional spacetimes. They're kind of scale, kind of fractal structures also. So no matter how big I make this, it will always keep looking like some big branched polymer and never have any dimensionality that is in any way close to 4. So it's a problem. See, then, well, realizing this, well, one thing was to say, well, maybe something interesting happened at this transition point. But upon looking closer, it didn't seem to be realized either. So it could, of course, be, there might be an appropriate second-order phase transition, people say, and you could be able to define an interesting continuum limit here, which might then have some larger Hausdorff dimension than 2. But it just doesn't exist. It's just not there. I mean, you look for it, and then you establish, of course, always, within measuring accuracy, that it's not there. So I want to make various points here. So one is kind of the invaluable information we can get by trying to make things quantitative to some extent, in a brute force manner, but you're just applying numerical approximation techniques, extracting information which you could not possibly have understood from just manipulating these path integrals, on paper. So here you get information, and the way it is, they give you a hint of what could be happening, and you then try pen on paper to do some computation, to come up with effective models. And this is it's a give and take between numerical and analytical. And the second thing is here, which is remarkable, therefore, and it's connected to my first point, you had an idea that this gave you a good theory of quantum gravity. But you have now more or less conclusively shown that it's just not the case. So you've disproven a theory of quantum gravity. And I would like to emphasize to you that is something rather rare, because usually you cannot even disprove these models you write down, and these proposals that people make. Yes?
What happened when we went off the critical lines?
Oh, yes. Yeah, then, so one needs to fine-tune it, essentially because the partition function only converges up here. So for sufficiently large lambda, the explanation is roughly speaking the following. This is my, let me leave out the 1 over c factor. Okay, so this is my path integral. These are all triangulations. I can split it up. I can split off a sum over n. And of course, what this is, roughly speaking, is the S of t. Roughly speaking, lambda times n minus kappa times r curvature, expressed in terms of my discretized data, my simplicial data. So in particular, I have the cosmological constant term here. And this lambda is positive. So what I have here is a minus lambda n. And what I'm doing then here is I'm restricting the sum to all those triangulations which share the volume n. And then here I have my S at fixed n. This is just a trivial rewriting of this sum. Now, one can show here that the number, and these are positive numbers. So here I'm just summing over positive terms, so positive real weights. And one can show that this behaves to leading order as a function of n. I'm interested in sending, of course, in the large n's. I'm interested. The leading order is exponential as a function of n. So, and of course, you are interested in the n equal to infinity limit of this whole thing. So what you see here is, to leading order, you have some competition between this divergence. Of course, the larger n, the more contributions I get. I mean, this is just like the entropy of the path integral. The more realizations of this of a geometry there are at volume n, and thankfully it's no worse than exponential in n. That also means that we have a chance to counter it. If we want to regularize it and renormalize, we have a chance to get rid of this divergence by fine-tuning this parameter. So if this lambda is sufficiently big, this exponential will kill this exponential, which just means you have a finite partition function, also in the limit. And this is exactly the region up here. If you're below here, then your lambda is too small, and it will always, the whole thing will exponentially diverge. Now, what you therefore have to do is you have to, well, another thing is, of course, what happens here is that as long as you're away from this line, it converges, but any large n contributions will be exponentially suppressed. So you also don't want that, because you want them exactly to contribute to your path integral. You want to take this limit n going to infinity. And this can then be achieved by fine-tuning to this line. So then you sit precisely on the convergence radius of this entire expression, which will enable arbitrarily large geometries as a function of n to contribute. Okay, so, and, well, so, loopholes are loopholes everywhere, but most people were happy to conclude from this that Euclidean dynamical triangulation is the wrong theory. And I told you, well, it's an asset to be able to disprove one's theories, but of course then one has to think further and try and understand, is there any way around it? And, well, there's another nice aspect, I would say, about these systems, is that they are very robust, and they don't have many free parameters. So it's not easy to just, turn a screw here and there to fix this problem. So, but there is apparently one way of nevertheless getting something more interesting out of this, which I'll tell you about tomorrow. Yes?
Is there a finite temperature interpretation of Euclidean dynamical?
Not really. Not really. Also, of course, what you're getting out of here is some kind of ground set of geometry of some effective dynamics. So you could ask, well, what are excited states? No one really knows. So, no, there are many open questions. Yes?
Can we increase the dimension of the original model?
Yeah, you can play the same game with building blocks. Well, starting with 2 dimensions, you have triangles. You can do 3, 4. I don't think anyone has tried higher than 5-dimensional. Interestingly, in these Euclidean models, it turns out this picture is generic for dimension 3 and higher. So you find this path, this phase diagram, and you find the same characteristic geometries in 3 dimensions, in 4 dimensions, in 5 dimensions. So, well, therefore, it's pretty much generic, and well, it's an entropic effect, so it's maybe not entirely surprising, but a little bit disappointing, of course, if you were looking here for interesting, 4-dimensional physics, quantum geometry.